thinking about it and y'all really need some kind of reinforcement at home, especially for all of you that have been sick over the last few days, the last week or so, and for those of you that unfortunately may get sick. Last week we started on chemical reactions. This week we're really going to dive into that even more. We have went through several months of chemistry to get to actual chemistry, which is now where we're going to be combining pure substances. Now, there are several things that you're going to need to know at this point, and you should know at this point, including the chemical bond types, how to write chemical formulas correctly, how to write chemical names correctly, the oxidation numbers, also known as the ionic charges. Now, you should also have readily available a periodic table and a list of the common polyatomic ions. Here's one like you have at school. You can find these online as well, very decent versions of both. Now, we're gonna take a look at several different chemical reactions. I want to point out some things that are important, some things that you should be doing using as guidelines as you write formula equations. A chemical reaction can be described in a very detailed way, but we can actually paraphrase it and condense it down into what we call a chemical equation. Now, there are 5 reaction types, and I'm going to start with the first one, which is called a synthesis or a combination reaction. I typically like to refer to it as a synthesis reaction. Now, a synthesis reaction is when you have 2 simple substances and you build them up, you combine them into one more complex substance, okay? So, for instance, if we were to have carbon combined with oxygen gas to form carbon dioxide. So carbon as a free element would be in solid form. It is a solid at room temperature. We add it to oxygen. Now keep in mind that these 7, nitrogen, oxygen, fluorine, chlorine, bromine, iodine, and hydrogen, all of these are your diatomic nonmetals. And remember, when they are in a singular form, that is when they're not in compound form, they must have a subscript of 2 because they are covalently bonded to an atom just like themselves. So this would be oxygen gas, and these would combine to form carbon dioxide. This is covalent. We know this because it's a nonmetal and a nonmetal. That's why it's called carbon dioxide. Those prefixes are used. And it's a gas. Now, last week we started talking about these little symbols that you're going to see occur in chemical reactions. These simply indicate the state or form that your chemical substance is in. Now, again, a synthesis reaction will build up simpler substances into a more complex one. Now, also something that I mentioned last week for those of you who weren't here and something we covered was that the yield arrow can give you details on the environment or the condition of the reaction. So for instance, if it's heated, you'll see this delta triangle, and there is a handout that I have online on my webpage available for you guys that were out that shows all these symbols. But this means that there was heat added to the reaction. If you see something like a specific temperature, then it's telling you that reaction occurred at that specific temperature. Important stuff, because otherwise the reaction may not occur without those set of conditions. Now, you might also actually see, and we saw one like this in class, where this is the element platinum, which is a transition metal here. If you see a chemical substance, whatever it may be, whether it's an element or a compound that is listed above the yield arrow, that is serving as a catalyst. It's not really involved in the reaction. It's simply speeding up the reaction rate. Now, also, you could see something like pressure written here, which usually means that the pressure has been increased. You may see something like an actual pressure reading, like or measurement, like 2 atmospheres, which is actually above atmospheric pressure. So if you see those sorts of things, then those are just details about the conditions. Now, right here, nothing like that's given, but be aware that if you get a descriptive sentence of your chemical reaction and these sort of conditions are listed, you must indicate it over your yield arrow. Now, we are going to be getting into balancing chemical equations this week, which is where we kind of look more at we do more of a quantitative analysis of the substances. That is, we actually look at the law of conservation of mass, which says that whatever mass you begin with, you have to end with, okay? We can't just get rid of it, all right? It's going to merely transform into different substances. So you could see here, if I was going to list the elements that are involved, I've got carbon and oxygen here and carbon and oxygen here. Carbon is right here. I have one, and then I have one over here. I've got two oxygens here and then two oxygens here. So this is what we call a balanced chemical equation. There is equal mass on both sides of the reaction. We can even look at it in terms of the mass. This is in terms of what I call the mole or even the atom count. But when you look at this, this is 12 grams. That's carbon's average atomic mass to the whole number. And then oxygen, this is two of them. Oxygen weighs 16, so that's 16 times 2. That's 32 grams, okay, of oxygen. And then here, we can look over here and see, okay, carbon, that's 12 grams. And then 2 times 16, again, that's 32 grams. So you can see that over here, we have 44 grams, which is 44 grams of mass in our product side, and we have 44 grams of mass on our reactant side. This is very important. This is why we balance equations, because we have to ensure that what mass we begin with, the matter we have in the beginning, it will be equivalent to what we have in the end. It's just new and chemically different. Now, again, I want to mention that this is a synthesis reaction. Some different textbooks and different teachers will call it a combination reaction. I tend to call it synthesis, but it's where you synthesize your simpler substances into a more complex substance. Okay, and then we'll look more at this mass, this quantitative analysis of substances as we go along in these examples. Now, I am going to switch to our next type of reaction, which is the exact opposite of a synthesis, called a decomposition reaction. A decomposition reaction is where you will start with the more complex substance and break it down into its simpler parts. Okay, so in a synthesis reaction, you end up with one more complex product. Here you start with the more complex product or more complex substance as your reactant, and then you break it down, because to decompose means to break down, and that's exactly what we do here. Okay, so here's an example of your decomposition reaction. Let's talk about and analyze our substances for just a second. I told you guys in our last unit how important it is to get familiarized with the substances, whether it's just an individual compound or now we've got multiple ones in reaction. So calcium is a metal. This right here is a group of nonmetals, a polyatomic ion. So if you look it up on your sheet, CO3 is going to be right here. That's going to be carbonate, okay? So this is carbonate. Calcium has a 2 positive oxidation number or charge, and this is 2 negative. So this explains why we have one of each in the formula, but this has been provided for you. But just to kind of bring that back and realize that's what we have to do in order to get our formulas, all right? Especially for the ionic ones, you have to balance the charges. Now over here we have another instance of an ionic compound, a metal and a non-metal. This is 2 positive. This is 2 negative, so it's a 1-to-1 ratio on the ions. Now, over here you've got a non-metal and a non-metal, so this is carbon dioxide. We use prefixes. There were no balancing the charges. They didn't lose or gain electrons. They're sharing. Now, in this particular compound, what has happened is we've taken calcium carbonate solid and heated it, that's what this delta triangle means, in order to decompose it into simpler substances, the calcium oxide and the carbon dioxide gas. Now this would indicate that the reaction is occurring, the formation of a gas. Remember things like formation of a gas, light or heat being produced, a color change, a precipitate forming, which is just a solid forming from a reaction, an odor being produced. All of these things are indicative of a chemical reaction occurring. So this would be one of those things to show that or support that here. Now, a decomposition reaction, again, is where you take one more complex substance, you break it down into its parts. Also, let's look at the quantitative side of this. There is calcium, and you've got carbon and oxygen. I have 1 calcium on the reactant side, 1 on the product, 1 on this side, now on the product side, 3 oxygens here. Now, I've got an oxygen here plus 2 more over here, so that is 3, all right? So this is balanced. There are no coefficients needed in order to ensure that the mass is equivalent on both the reactant and product side. It is clearly already there, okay? Now, the next type of chemical reaction I'm going to share with you guys is what we call a single displacement reaction. Now, single displacement and double displacement, we'll get to in just a second, involve ionic compounds, okay? It's where ions switch out, okay? Now, in a single displacement reaction, use that word single to guide you, because in the basic format of a single displacement, you have a single element plus an ionic compound, and then you form a new compound and a new single element. So you will see that single element with the compound on both sides of the reaction. Now, some things to note about a single displacement reaction are that a similar ion will replace the ion of its kind within an ionic compound. So we'll show in the example that I'm going to put up here in just a second, you'll see this. Now, this is where the partner is dumped. This is kind of the unfortunate one. The double displacement is a much better reaction, but it is the one where one of the ions does kind of get the shaft. Now, and again, like I said, single element in a compound will yield a new single element and a new compound. Now, I'm going to give you an example up here with iron, Fe solid, and copper 2 chloride. Now that Roman numeral 2, I'm saying in its name, indicates it is a transition metal that has a varying oxidation state. So if it's copper 2 chloride, that means it's 2 positive. Now chlorine always has a charge of 1 negative, so the correct formula for copper 2 chloride is CuCl2. Now, copper 2 chloride, it's a copper 2 chloride solution. Now, AQ is a term that means it's been dissolved in water. It means aqueous. So if you've got a solution that's been dissolved in water, we've indicated with an AQ. Now, these will react to form copper solid and iron 2 chloride, okay? And this is still an aqueous. It's still dissolved in water. Now, this reaction shows you that you have a single element that comes in and replaces, this is a cation, it is a metal, so it naturally will be replacing the metal that's in the compound. So you take this metal, you replace a metal that is apparently not as reactive, so iron will take its place. Now you've got this new lonely single element, and iron has now replaced it. So it is where the in the compound there is a new partner involved, okay? So let's look at the quantitative side of this. Iron, we've got 1 here and 1 here. We've got 1 copper here and 1 copper here, 2 chlorines here and 2 chlorines here. So this is balanced. There is equal mass on both reactant and product side, so we will not need to balance this one either. Now, this is a single displacement, sometimes called a single replacement. So you might see that word used, it means the same thing. Now, a double displacement or a double replacement, it also has that term that can be used instead of displacement, is where you've got 2 compounds that will basically swap partners. So this is a happier ending because you don't end up having someone that's been replaced and now on the outside looking in. This is a mutual, what I call a mutual partner swap, okay? Now, the reaction that I'm going to give you for the double displacement reaction is barium chloride. Now, barium is a 2 positive and chlorine is a 1 negative, so this should be BaCl2, okay? Now, this is in a double displacement, it's where you have 2 solutions where ions will swap. So typically in a double displacement, this entire thing occurs in solution, so your substances are going to be in aqueous form. Now, and you'll see this in your descriptive sentences when the reaction is being described. All right, so we've got this plus sodium sulfate, okay? Now, sodium sulfate, Na is sodium. Sulfate, that means it's a polyatomic ion. Sulfate is SO4. Now, again, do not just write down your formula and say, oh, okay, I'm done. This is definitely a metal and a group of nonmetals, meaning I need to balance the charges. So this is going to be 1 positive. Sulfate has a charge listed on your reference page as 2 negative, so that means I'm going to need to have a 2 right here to indicate the balancing of charges, needing 2 sodiums for every 1 sulfate. Now, this is in solution. to produce, now this is a partner swap, so that we're just going to take these metals and swap them, okay? So now sodium will be with chlorine, and again, I don't get to carry over, oh, well, there's a 2 over here, so there's got to be a 2 on the chlorine over here. Doesn't work that way. You broke all the bonds, you're creating new ones. So do not defy the laws of formula writing just because you want to make sure you've got 2 and 2. That's not the way it works. Sodium is 1 positive, chlorine is 1 negative. So this is just NaCl. And then our other new compound will be barium sulfate. And once again, do not assume that, oh, I need 2 of these since I needed 2 of these with the sulfate. That's not the way it works. When we create ionic compounds, we've got new ionic compounds we're creating. The cation to anion ratio within the compound will be based on their oxidation numbers. Barium is 2 positive, sulfate is 2 negative. The 2 positive and the 2 negative cancel each other. They equalize or make this a neutral compound. So they balance each other out. So you just need 1 of each of these. All right, and this is also in solution as well. So this entire reaction is occurring within a solution, okay? And you can see this is the metal replaces this metal, so you just do a partner swap. Now let's take a look and see, are we balanced? I've got 1 barium here and 1 barium here. I've got 2 chlorine here, but only 1 here. Okay, so let's go ahead and list, and we'll do this more in the upcoming week on balancing and the rules for balancing chemical equations. But barium, chlorine, sodium. Now I'm going to tell you guys something here, and you need to kind of use this. This is going to be one of the kind of the guidelines we follow with balancing is if you have a polyatomic ion that keeps itself together, that is, it doesn't get broken apart from one side of the reaction to the other, then you just count it as 1 unit. So what we would do here is just indicate sulfate like this, okay? Don't break it down into sulfur and oxygen. Trust me, it's going to save you a lot of heartache as we go through practicing with balancing equations. So you're just going to kind of count this as its own little unit, its own little atom. So I've got 1 barium, and like I said, your chlorines are off. We've got 2 and 1 over here. We've got 2 sodium here, but only 1 here. And then our sulfates, there's 1 of these, and then 1 over here as well. Remember, with your polyatomic ions, if you have multiple ones, then there'll actually be a parentheses around it and then a subscript to indicate however many you have more than 1. Okay? Now, in order to fix this, I cannot go down. I can only work this side up, okay? Because writing coefficients, which are these large numbers in front of chemical compounds, will allow us to increase our mass for those atoms, or for our atom count if we're looking at it this way. So I need 2 more of these and 2 more of these, so I can place a 2 here. Now, you always place the 2's at the beginning. You can't go around rewriting subscripts either, so don't ever do this. Okay, that's not allowed. You're defying formula writing technique. We've never done that before. Sodium chloride is just NaCl. There are no subscripts there. Okay, so you would have to put a 2 coefficient. That indicates that I've now got 2. You're distributing this 2, and so I've got 2 sodiums now, and also 2 chlorines. So I've fixed my problem. I now have equal mass over here and over here in the product side. Now, someone asked in class last week, they said, what is the difference between this and then the subscripts here? Well, there is a really big difference, because what we're saying is we've got 2 sodium chlorides. That's what it means. It's 2 moles of that compound here, okay? Whereas over here, we've got a barium, 1 barium atom, and then 1 sulfate ion. Over here, we've got 2. That 2 means I've got 2 sodiums combined in compound form with a sulfate ion. And then I've got 1 barium atom with 2 chlorines. So this is 1 mole of barium chloride. This is, because this is a 1, there's an understood 1 here, but we don't have to write these, okay? And we did have to write the 2 here to balance it, but that means I've got 1 sodium sulfate, but then I've got 2 sodium chlorides, and then I've got 1 barium sulfate, okay? So what you see here is I've got 1 of these for 1 of these will yield or produce 2 of these and 1 of these, okay? So the coefficients are representing our molar quantities. 1 mole of this added to 1 mole of this will create or yield 2 moles of this and 1 mole of this. The individual subscripts are referring to the actual atoms. They belong to just the atoms, but the coefficients belong to the entire compound. I've got 2 of this entire thing, okay? Now, this is your double displacement reaction. Again, similar ions switch places. It's a mutual partner swap. Everybody's happy. You have two compounds, and then you get two brand new compounds. Okay? Now, your last reaction type that we're going to go over is actually the easiest to recognize, and it's called a combustion reaction. Now, a combustion reaction is when you burn fuel in the presence of oxygen to create carbon dioxide and water. The only thing that changes from one combustion reaction to the other is the fuel type. So your hydrocarbon will be different, but otherwise you'll always have oxygen gas as a reactant, and then your products will always be H2O, water, and CO2, carbon dioxide gas, every time. So the only elements you'll ever see present are carbon, hydrogen, and oxygen, CH and O. Now, I'm going to give you an example with this. It's going to be methane gas. It's a natural gas combining with oxygen gas. Remember, oxygen is one of those non-metals that will actually combine diatomically, what we call diatomically. So you always have to put a 2 next to it, okay? Now, this right here would actually be what we call carbon tetrahydride, would be its actual formal chemical name. Now, I call it methane because that's its more common name, and I know it is that, but you might not know that. And that's okay. You would just name this as carbon tetra because this is a non-metal. With a non-metal, we use prefixes. Carbon tetrahydride combines with oxygen gas to yield, to form, to produce. All those words mean the same thing. Water, H2O, and carbon dioxide. Now, actually, this may be a water vapor that actually is released, so it may be more appropriate since it's being burnt to actually put a G there. All right, so this is our combustion reaction, and again, this is the only thing that changes. The only substance that changes from a combustion reaction to another one is this right here, okay? So just kind of keep that in mind. Otherwise, you should be able to recognize this one all the time. It's very easy to recognize. So now it's time to do a little quantitative analysis. That is, look at our quantities of, in terms of atoms, and this really our mass. You've got carbon, hydrogen, and oxygen. Those are our 3 elements, always in a combustion reaction. That's what makes these easy. So I've got 1 carbon here, 1 carbon here, 4 hydrogens here, 2 here, and then 2 oxygens, and then 1 oxygen plus 2 more. There's 3 over here. Now, we want to look at the ones that are not balanced. Usually we don't balance hydrogen or oxygen to the very end, but those are the ones that we seem to have problems with. So let's address them. First of all, the hydrogen, I've got 4 here and 2 here. I'm going to bump this up by putting a 2 coefficient in front of the water. That means now I've got to have 2 water molecules, basically. 2 times 2 is 4. 2 times 1 basically is just 2. So there's 2 oxygens here plus the 2 more over here. So that's now a total of 4 oxygens. So now all I need to do is fix my oxygen on the other side where I've only got 2. I can't just make this a 4, okay? Understand that you can't mess with the subscripts, all right? The subscripts are set. Oxygen is diatomic. It always appears like this, okay? So in order to actually increase this to 4, we just have to put a coefficient that'll make it 4, which in this case, a 2 will do the trick. 2 times 2, this is 4. Now we have equal mass on both sides of the reaction. This is balanced, okay? So we have correct formulas. We have a balanced chemical equation. We have details about our states of matter. So that is your last and final type. Now, one more thing I want to review with you guys really quick is our conversions between grams and moles, okay? So if I were to tell you that there were 34 grams of water produced, okay, in this reaction, and I want to know how many moles is that, okay? So don't forget about doing these. We had this on our last unit test. And I wanted to just kind of bring it back up because it's really going to start playing a role throughout this unit and our next one. If I want to know how many moles this is, then I need to make just a quick grams is a unit that we use for mass. Moles is a unit we use for chemical substances. So they can play a role together simply, or they play a part together by the molar mass on the periodic table. So if I look at this, I want to get out of grams and go into moles of water, okay? All I would have to do is say, okay, 1 mole of water weighs how much? Well, each hydrogen, according to the periodic table, weighs around 1, okay? So that's hydrogen. There's 2 of them. They each weigh about 1.101 grams. We'll keep a few decimals there. And then oxygen is, there's only 1 of them. It weighs 15.9998, so we're going to round that up to 16.0 grams. So 2 times this plus 16, you should end up with a mass of around 18 grams, okay? I have a couple of decimal place values that's going to give me a little more precision in my answer. So once I do this, the grams will cancel, and so my answer would be 34 divided by this, where your calculator is going to come in handy, because the simple division and multiplication isn't fun to do without your calculator by your side. So I get 1.8878. I've got 2 sig figs here and 4 here, so I'm just going to round to 2 sig figs. So 1.88 is going to round to about 1.9 moles of water produced, okay? So don't forget your molar conversions. You've got to be able to look at quantities. You're going to have to know the difference between, this is how many O2 molecules I have. I have 2, this is just another way of looking at this. I've got 2 O2 molecules. I've only got 1 methane molecule, okay? And then that yields 2 moles of water and only 1 mole of carbon dioxide, okay? So this is really what we're looking at. So if you want to know the difference between a coefficient and a subscript, the difference is, this is just the individual atoms within the molecule, within the compound. This is how many you have of that entire thing. Okay, and so again, last reaction type, it's a combustion. This is our quantitative analysis piece, and that should bring you up to speed between late last week and then what we're going to be doing in block periods tomorrow and Tuesday, whenever you have me, and we'll move on to balancing chemical equations on Wednesday. Come here, Chase. You want to say hey to everybody? Come on. Come on. All right, just wave at Mommy's phone. Say hello. Okay, all right, so hopefully everyone gets better, gets well, and I most likely will have a follow-up video on balancing chemical equations.